Okay. Okay, I'm going to start my talk today. It's, let me get, excellent. Okay, so we are live. I hope everybody can hear us. So today my talk is going to be about inspirational applications of AI, artificial intelligence. Okay, I have been invited by the Sustainable Education Foundation to talk to you. So good evening. Um, yeah, so I want to first start by introducing the subject of AI and how it works and some implications for uh, technology and how to practice it a little bit, as well as some of the most important aspects of how AI can help us. Okay, so hopefully it will be inspiring and you can learn. The technical level and the depth is going to be at a fairly sort of not an expert level, so I hope you can follow me. All right, so let's start by asking the question, what is AI? Okay, so the word AI was coined by people only in 1955, right? Before that, they were doing some research. It was a sort of subfield of computer science, and it's still a subfield, but they had not coined the word. Uh, so, as you can see from here, the average person wants to know, can machines think, right? So let's try to answer that and see how that statement relates to the modern day concept of AI. Okay, so this Time magazine cover from 1996 shows you, people asking this question is about 22 years ago, and the answer here says that some scientists say that it's already here. Okay, they mean 1996. So since then, actually, AI field has gone through sort of a what I call starvation period, like a famine. Basically, the techniques that work in 1990s are no longer promising. Okay, so people were doing research till about 2012, and then we had a major breakthrough. So that after 2012 to 2013, only we have started getting a lot more excitement, because now it appears that we can measure or at least under, solve problems of computer vision pretty close to the accuracy of a human. All right, so let's look at the word intelligence. Intelligence obviously is a very difficult word to define, but it is the ability to acquire and apply knowledge and skills. Okay, so that's how the dictionary defines it. And so I think here you can see we can define two different things. One is a special purpose. That is, can we build a system or a machine that can achieve a well-defined finite set of goals? And of course, the answer is yes. So this could be very much like a handwriting recognition system. So it only knows how to recognize digits, for instance, from 0 to 9, and so it can read your check, and so you can take a scan of your check, and then we can at 99.9 accuracy tell what digit you have written. Okay, so that a bank can use that to automatically deposit your check. So that's a very special purpose one. So we wouldn't normally call it intelligence, but yes, it will, it will satisfy these criteria, right? Achieve a well-defined finite set of goals. The second one is, of course, is more general intelligence. That is, can it achieve a poorly defined, unconstrained set of goals? maybe at this point. Okay, for instance, can we build a robot, let's say a robot postman, to take a bunch of letters and go and deliver it to all the houses in a street. Now, when you try to do that, there is a lot of unconstrained things. There could be people might gates might be closed. There could be dogs, whatever, right, on the road. So it's a much harder problem. But its goal is to deliver all the letters. So can we do that? At the moment, it's a maybe. So if you look at this picture here, this is how you need to. This is a very nice picture that shows what is an AI. Okay, artificial intelligence. So here, this is some abstract agent. This is could be a software program, could be a robot. Now, what it does is it looks at the world, and so it's essentially a perception. Okay. Oh, so perception is what we see here. I'm sorry. When the agent looks at the world, and what it does is it perceives how the world is through its senses. Okay, through its senses, and and then something goes on here in this box here, which is a question mark here, and that's where the AI runs. And in the AI, you can see it will take some decisions, and you have these actuators or effectors that actually take actions on the environment. Okay, that's how a robot functions. So essentially, it's very similar to how we function, but this is the most simplified view. This gives you so the AI is running here, right? Everything else is well understood. Uh, you know, this is a cause, and this is an effect that we do with our AI agent. So I want to before I want to go through here quickly. How do we know that we've built a good artificial intelligence? Okay, so this is a picture of Alan Turing in 1950. He was able to come up with this 1952, I think, thing called Turing test. He's one of the founders of modern computer science, along with John von Neumann, others. You must have heard about him. So a Turing test is a test of a machine's ability to exhibit intelligent behavior to or indistinguishable from that of a human. So the idea here is that we have humans here and we have intelligent behavior here. Okay, that is machines can have intelligent behavior. Now, not all human behavior is intelligent. Humans may uh, you know comb their hair or something, and that's not necessarily intelligent. But we are also capable of intelligent human behavior. And here we see intelligent behavior of machines, and machines can actually do certain things like back up yourself, so that you don't lose all your work, which humans can't do. So that I would say is intelligence. So there's a subset here. That's what the Turing test is focused on. And so how we administer the Turing test is that you have some observer, a human evaluator, and you have a human answering some questions. So the evaluator will ask certain questions, but he doesn't know whether the answer is coming from a computer or a human. And so he can ask whatever question he wants, and if both of these guys are answering in such a way that the human can't distinguish it, then you pass the Turing test. That is, the machine or the AI is as good as that, as good as the human for that purpose. Okay, so a general purpose Turing test passing machine is not currently there, although some people have some marginal success there. In 2013, they tested with a 13-year-old boy, but a computer can't even act like a 13-year-old boy in most cases. Okay. So what I'm trying to tell you here is that as AI becomes mature in certain subfields, so because we won't have general purpose intelligence for a very long time, but we will have a very good intelligences. For instance, AI can play chess, for instance, better than any human player in the world, actually. The world champion, I think, will be a chess computer at the moment. So then, obviously it passes the Turing test because, it doesn't play any worse than the human. So in the same way, we are trying to do medical diagnosis. I'll talk a little bit about it by let's say reading X-rays. So if the computer can read an X-ray and diagnose better than a human doctor, or as equal, in this way, then we will accept it. So we can apply this Turing test. Okay. So main point is superhuman accuracy is not needed. It's nice to have, but most times the computer will be superhuman because it will do the task in a few seconds when the human needs few minutes or half an hour to do the same problem, right? So just matching expert ability is sufficient for success. Now I'm going to talk a little bit about emerging use cases for AI. And AI is important today because of our mobile phones. In mobile phones, we have various tasks like motion stabilization or video stabilization. That means as you're driving around, and if you take a photo, it's blurry, and then you actually can use some AI to make the picture clearer. Face detection is one. In this case, dynamic range. Yeah. So in this case, basically auto adjusting the contrast of the picture. In automotive, right? In cars, AI is going to be very, very heavily used because we had things like cruise control. Now we are going to a more autonomous cruise control, and I will talk a lot about this. But we need to understand these signs and all these other things, right? So we have we have that, and gesture control. So all of these are places where we can use AI, and then of course drones. And I think for delivery of packages and other things. Security, basically, there is a lot of jobs currently just looking at a passive security camera, could be your office or your home, and looking for intruders, who's coming and going, and sometimes you can even identify them by face. So those are very tedious human tasks, but can be offloaded to a machine learning or AI. And then there are some applications in wearable and IoT technology as well for AI. Okay. For anomalies, for instance, if your heart rate is anomalous, then alert the doctor and that kind of thing. So ubiquitous mobile phones and cameras imply basically that machine learning or AI is able to run on. I'm sorry. We need AI algorithms and machine learning to run on mobile processors. The field is going to be a big field because there is already more than a few billion smartphones in the world, and they will all require solutions to these problems that I'm talking about, and AI is a good solution. And that's why the field, one of the reasons why the field is growing. All right, so here's the industry growth projection. So we are now at 2018, and by the end of 2018, the projection is about around $2 billion of revenue generated in this field. But you can see by projection is that by 2025, which is about another, I think about 8 years from now, or 7 years, it will go to almost 40,000. So there is a big factor here, at least higher than a factor of 10, right? Almost a factor of 20. So it's a 2,000% increase in the next 7 years. So it's a very exciting field. It's one of the growing fields. So I think it's very relevant that we study it and try to become experts or learn how this thing works and what impact it's going to have on our lives. All right, so now I'm going to talk here about why is this growth. Okay, so one is that it's driven by the wide availability of data. There is exponential growth of data. Everybody is now well, the data is available now on the computers and the smartphones. Companies like Google and perhaps Facebook and others will try to capture this data, but also it doesn't have to be just those companies, but every enterprise has a lot of data, right, of their own domain. So, and these are growing in terabytes now, so I think it's data availability is one of the first drivers. Second is that the algorithmic advances in machine learning. All right, so about we can now build models with 10 million parameters, and that's not unusual. That typically we can't, humans can't build like even having 2 or 3 or 5 variables in an equation is quite complicated, right? But here we can make models that essentially captures 10 million parameters, so we can model the real world quite well. Okay, so that's the reason. It's the advances in the algorithms. Fast machine learning capable hardware is available now, where these are called general purpose GPUs, but mobile machine learning accelerators are available. These are hardware that can do maybe about close to 100 times faster than a normal CPU for specialized mathematical operations that are required in machine learning. And also, one thing that's really very key for this growth is that there is no need for hold on, no need for large infrastructure. Okay, so let's think about how broadband happened, or even the cellular mobile phones happened, right? So a lot of companies had to go and put cell towers or dig the ground and put a lot of cables and wire up your home so you could have a megabit connections to the internet. That costs a lot of money, but for the machine learning revolution, you don't need that because it's incrementally riding on the currently existing infrastructure. Anyone who has a smartphone, who has a computer and an internet connection with sufficient bandwidth is able to now contribute and leverage the machine learning. So this is an important point, all right? So let me go and quickly explain. I think I need to put, just give me one. All right. So, okay, so what is machine learning? Okay, so this is traditional programming. Okay, everyone knows hopefully how a normal program works. That is, you have data coming in and you write a program. For instance, the example here is calculating a square root, okay, which is not easy to do, but it can be done with a computer. And there is a thing called an algorithm. I will go through that. But so what we do is on the computer, we write a program that from the data, the input, we calculate the output, which is the square root of the data. All right. So if you put 4, you get 2. Okay. If you put 9, you get 3 or whatever, right? Now in machine learning, it's completely the opposite problem. What we are trying to do is we have data and the output. So we are going to put in 9 here. And we also know that the output needs to be 3 because it's the square root. And we are going to ask the computer to calculate a program that works. So tell the computer to write the program. Okay, I mean not write the program, but the scheme. Okay, so that anytime you're given a 9, it will output this program will output 3. Okay, and that's the goal. So essentially, in a nutshell, the old way is to program implements algorithms in traditional programming languages, like it's called coding. It could be C or Java or whatever, and so you write the program, okay. And an algorithm is just a simple scheme to get at the answer, and obviously everybody knows an algorithm. For instance, long division is an algorithm. Okay, you learn it in second grade. Third grade. You practice it. It's a scheme. You don't know why it works at that age, but you just memorize it and you know how to do long division. In the same way, an algorithm is the scheme that calculates, in this case, the square root. Okay, so we need algorithms for machine learning. Now, how to generate the program, that is to map the input to the output, right? That's what we want to do. Okay, so from data and output, input and output, we want to create the program. And so this is called a machine learning algorithm. Okay, and what we do is once we have the data and the output, the program is written, then we immediately go and feed that back to our traditional type of thing. And so this is called training. In machine learning, there are two kinds of steps. First thing is the training step, which is to come up with the scheme. And it's essentially a curve fitting scheme in this case, to calculate the square root. So this program out, you feed that into this guy, which is what we want. We want is the output. So this is called inferencing. Okay, so basically you use the program output of the machine learning. I'm sorry, use the scheme that you generated and you show the input and infer the output. Okay, that's what machine learning is, and it's nothing more than that. So it's a little bit different thinking than a traditional, code, right? Coding problem. So a lot of times these days people talk about deep learning. You may know this, but I'm going to summarize this very quickly. The AI field is broken down. This is like a Venn diagram. So this is the subset is here, machine learning, right? Machine learning is a subset of AI. And in machine learning, there are two kinds of algorithms. So the one that is getting most popular these days is a thing called deep learning, which is to use, I will explain this in the next slide, but this is the key innovation I talked to you in 2012 that allowed us to achieve sort of human level image recognition. Contrast that to the unsupervised learning that a child does, right? So we are not very strong in this part yet in AI. Okay, what is gaining traction is here, but one would think that there are some algorithms here, but it's important that more research and development get done here. So the deep learning, the word deep comes from that you will see having a very many layers in a neural network, which is a type of which is type of network that we use for curve fitting, and so the deep learning gives you very close to 100% accuracy for many problems. I'm going to quickly go through. This is my most technical slide. Bear with me. And here, I want to show you what this is sort of a network diagram here. So let's look at one of the layers of this network here. Input is here. First, what we do is we convert our problem, even recognizing a face, okay, whether it's your face or your friend's faces, we need to convert the problem into a numerical problem first to use the computer. So input features of the problem are numerically represented, inputs and outputs, right? This is the layer A here. And we just multiply by some weight matrix, okay, that is numbers between 0 and 1, randomly chosen initially, and then we sum it together and with a bias with another number, and so there's some math here to give you intermediate input. And so this part is a linear operation. That means matrix algebra, all right? And then we do need a nonlinear activation function, that is when a certain input is high, when you want to tell that the output is high. Okay, so you basically need a nonlinear operation, and there are many examples of this function that we can use. But main thing I want to talk to you is that we need a linear operator and a nonlinear operator for each layer. Okay, because if you just only had linear, then you can just keep multiplying matrices to the one after the other, and you still get only linear, right? And that won't be able to learn anything. So stacking linear and nonlinear operations, and then a training procedure, which I will not specify, but is essentially using a Newton's method for finding square roots and things. That's in generalized. It's called gradient descent, and that's what we use for training neural networks. Okay, so it's a little bit of math there. Now, with all these techniques and with deep learning, what we find is that we now can beat the expert human level. Okay, so deep learning seems to approach or exceed the human recognition level. Secondly, um, in after 2000, well, sorry. So after 2000, this is the sort of the landmark paper where people before 2012 for image recognition. So this test is a very good test. It's has a 1.5 million or 2 million images of various objects, and there are 1,000 objects. Various things like cars, computers, cups, dogs, clothing, and animals, and various 1,000 objects that you will encounter in real life, and computer has to tell whether accurately identify. And I have an example I'll show you later. So before that, this is not the accuracy, this is the error rate. Okay, so accuracy is 85% here. Error is 16, right? 100 minus the error is the accuracy. Earlier, it was like, error rate was 40% before 2012. So this is a big improvement with the first deep learning model. People have improved this thing now over the years in this, and now after 2015, we can get to better than a human accuracy for image recognition. This is a huge thing because, here we are talking about, identifying cats and tigers and dogs and, all kinds of objects that you would see. And so now we can read pictures and tell what we have. Okay, so it's very, very exciting. So I want to get to a couple of interesting applications of this. Okay, because my talk is essentially about interesting applications. So I'm going to tell you a little bit about some fun applications here. Um, so I think this is, let's say you go to a foreign country, and I think this is in Danish, but in Denmark probably. I might be wrong, but so you see this thing, and then it would be very nice, as you look through your cell phone or augmented reality application, if it can automatically tell you what it is, So essentially, we can do that. Okay, so it's essentially using Google Translate in this case, which also uses AI in the back end and recognizing signs, extracting the letters out of here, and converting them with AI, and then now it's very nice. If you no matter where you go, you see a lot of street signs and advertisements in all kinds of foreign countries, and now you will be able to read them in your native language, which is a huge application, in my opinion, if we can pull this off. And I think people are getting very close. And in the next 5 years, this will be done using machine learning. All right. This is the ImageNet puzzle I told you about. This is the 2012 model, that had only 85% accuracy. I don't want to go through the structure of the network, but it has many layers. That's why it's called deep. Each of them is complicated mathematical operations of convolution, so they're called convolutional neural networks. And convolution is a mathematical operation that try to match local structure, okay, essentially. But let's look at the results. This is very interesting. So this is the confidence of each prediction. These are the top 5 predictions. So in this case, as you can see quickly, you can see that it's a container ship here. And so obviously the computer, the ImageNet algorithm gets it right, and with a high probability here, right? About 80% here. But it also, its second one is also not so bad. It's a lifeboat, you know. So between these two, it's pretty sure. So in this case, this is like a scooter, motor scooter, I think. So they get it right here, a go-kart, moped, bumper car. So if you, all of these are quite reasonable, I think, just by looking at this picture. So you're getting, you know, if you add up all of these, the first 4, what it could be, you know, is pretty good. I think around 99% accuracy, 95% accuracy. Again, this is a leopard, and you know, for me, I can't tell whether it's a cheetah or leopard. I'm not that an expert, so I think again you can see the very reasonable suggestions here. Okay, so we are able to then um, identify and recognize real world objects like mopeds and, you know, fireboats and other things like Egyptian cats. Okay, so that's pretty good. Another very interesting one, maybe not that much of huge commercial value, but is that we can train the machine learning algorithms to colorize pictures from old black and white films, and then you can see it's pretty good. And you know, I think over the next few years we will improve these algorithms, keep training with new data and better data, and we should be able to you know, um, get yeah, see all the old movies in color automatically without you know, because it will infer a color and color it properly and make it look good enough for us. Okay. Here is how this thing works a little bit more. This is called image caption generation, and this is also very important because nowadays everybody's taking a lot of selfies and other things, and then, you know, we have terabytes of data, and we don't know, like, you know, we want to tell our cell phone or your you know, show me a picture when I was holding an apple, or when I was at the Eiffel Tower, or something like that, right? Because otherwise you have to go through, you know, in the old days you took only maybe a few dozen photos, but nowadays people take 1,000 pictures when they go on vacation. So we have too many of them. So we want to be able to ask the computer, okay, show me when I was holding a dog or whatever, right? So in this case, this person here is holding a dog on his lap, and so the way the algorithm works is it makes all kinds of sentences and then tries to score the sentence. And also at the same time, here, when the word dog is highlighted, you know, it shows the dog. Okay, it's red. Red means high probability that the dog is here. Here it says the man. Man is here, so it recognizes face. Okay, sitting. When the word sitting is triggered, yeah. So you can see the chair, and then obviously it knows that it's sitting because of the chair and the man here. And then here it says there's a couch here, and it also knows that there's a couch here. So it's an extended object, and it has learned that there's a couch here. So it puts out various suggestions, like a man sitting on a couch with a dog, a man sitting on a chair with a dog in his lap, you know, and there we have another algorithm after that going and scoring and trying to give you the best. Okay, so the same way here for this lady here. So the number 1 suggestion is that a woman holding a camera in a crowd. Okay, when you see that, so because it knows there's a crowd, knows this purple here holding camera, and there's a misidentification of her hair as a cat, but nevertheless we are able to make this kind of inference of what's in this picture. That's quite impressive. So questions, images answering, basically image question answering. We are not quite there yet in terms of our ability to, yeah. So this is quite interesting. These are three different models, and we are asking what is the color of the cat. Okay, so obviously it's black, and two of the models are saying 55% probability and 73% probability it's black. But what's the color of the couch? So some of the models are sure about it as 65%, but some of them are not. Okay, they're only 44% and gets it wrong. So when it gets it wrong, it's red. Okay, so green means it's correct. But here you can see where are the ripe bananas sitting. Answer is the basket, and so it gets to the basket. So another one says it's a bowl, but it's quite reasonable. Um, in my opinion, it's good enough for this purpose. But we have to be much higher accuracy. So sometimes some of these things, what are in the basket? So some of these models are not quite sure. They're only 14% sure that there are bananas. So we have a ways to go here. Okay, so it's a quite interesting little application, and want to show you where the current state of the art is. This is a 2015 paper, but I'm sure people have made more progress now, but this is still not 100% solved. Um, Again, object localization is important because the real world is made up of not just one object, but there's so many objects here. As much as 20 or 30 or 40 objects are typically recognizable by the human brain or human eyes. So, for instance, it's very important in traffic. And these are like some deep layers. So you can see deep meaning there are many layers. Okay, and as you increase the number of layers, then it becomes more accurate. Okay, so another inspiring application that is quite interesting is a artistic style transfer. Okay, I think you may have seen this. Again, this is quite a common slide for showing machine learning, but basically, these are three pictures here, okay, of three cities. This is San Francisco here, probably Amsterdam or some European city here, and some garden here. And these are three different artists. You have Vincent van Gogh here with his famous painting, and there are other ones here. As you can see, these art have a particular style. So what we can do is we can give this image and ask it to learn the artist's style and then re-render the picture for the city, or in this case the Golden Gate Bridge here, as if in the style of Van Gogh. So it's quite interesting. So what we find is that the content, that is what objects and all that stuff, is in the higher layer of this CNN network that I showed you, and the style or the texturing style is learned in the lower layers. So this is very, very interesting how it all works. Okay, but you can see it's quite interesting, and you can make very good art with this thing. I think a more serious and interesting application is detecting cancer, right? So there are about 2 million people, at least in the United States, dying of lung cancer. I'm sure worldwide it's probably 10 or 15 million or much higher every year. So to detect lung cancer. So this is think of this as a three-dimensional X-ray. This is called a CT scan, and this is a GIF, so it cycles through, and so we can tell that a patient may have breast cancer. I'm sorry, lung cancer here or not, and I think it will mark it in red when the cancer is there. There it is. This is a cancer here. Okay, all right, and so to recognize that, we can train the machine to do that. Of course, there are not every little white thing is they're just air passages and arteries inside not arteries, blood veins inside the lung, right? But these are the lungs as you go across. So you can see that you can detect cancer. All right. Also, you can detect breast cancer. I'm sorry, it should be BRES. Oh, sorry. Breast cancer. I misspelled it here, but breast cancer. And so this region here is the cancer region. So this is a slide of a tumor. You take it and you slide it and put it on the microscope and put some dye to stain it a different color, and the cancer stains differently than the normal tissue. and you can kind of see where the cancer region is. Okay, so we blow this region up here, and you can see that in the cancer region here, which we call the metastasis, I think. This white thing is fat layer, fat. Uh, these are cells, and in this case, because of the cancer, the cell nucleus, the cell wall, I mean, I guess the boundaries are kind of, it's broken up, and it's all messed up here. Okay, so the cells are not as well defined as the normal tissue, and we can get this idea to be taught to the computer, okay, through deep learning algorithms, and therefore it will assist us at 90% accuracy in detecting breast cancer. Okay, all right, so that's good. Autonomous driving is another huge field that AI will play a huge role in. This is a video of what an autonomous car would have to recognize. It has to recognize all these things: buildings, people, cars in front of you. And so if you look here, it's only 2 frames per second. So it takes about, 3.8 frames per second. And so about 2 to 300 milliseconds with a very fast computer. So that may not be enough yet. We need about 20 to 30 frames per second for human level visualization. But you need to not only understand the picture here, but determine where each thing is going to be, whether it's going to stop or start or go do something random. So this is quite a difficult thing. So some models are developed in 2016, 17, 18 timeframe. Google has a Deep Lab version 3. Some simple, very fast models are there called YOLO, and then Mask, RCNN. I think it's a Facebook model. So these are what state of the art image segmentation. So it not only recognizes the image, but segments the image here with different color when it's a human. And so this is the current state of the art where we are. Okay, sorry. Now let's get into autonomous driving quickly. Yeah. All right. I think we have a little bit more time here. Okay. So look at this left figure here. Okay. So if you're in a well-defined road, where people are staying to their lane and stuff like that, then it's quite easy. You only have 5 things to do. Okay. You either speed up, slow down, or stay at the same velocity, or go to the left or go to the right. Okay, there are 5 things, and you can decide what to do and to get to your goal, which is to go forward as fast as possible or as safely as possible. So that's a much simpler thing to do. So I call it easy. Okay, and there are many techniques to use. Some reinforcement learning techniques can do that. But in this case here, as you can see, in real life, this probably is somewhere in New Delhi. A picture, I'm not really sure where it is, but you can see it's a big mess here. If you're an autonomous car, then you have to figure out when is it your turn to go wherever, right? Okay, so that's the challenge we have. Okay, is that the real world is complicated. It's not like this left side here. So human performance is about 1 fatality in about 100 million miles driven. Okay, so it's about 160 million kilometers driven, right? We have to handle. So if you're not as good as this, then we can't put the autonomous car on the road, because you'll have more fatalities, and that's not good. But the idea is that you can reduce it by even a factor of 10 and get to 1 billion miles driven and have only 1 fatality. Okay, so we will get there. I think it takes time. Handle heavy rain, fog, snow. These are challenges. And of course, unpredictable human behavior, like opening doors and other things, while you're stopped, so you need to figure that out. Now, one problem is that AI sensors are vulnerable to attacks. So if you are a car, this is going to be tricky. Okay, so first let's look at this one here. A car is using what we call LiDAR. It's like a radar, but using light, so it's called LiDAR or laser for detecting objects and their distance. right? Visualization doesn't give you accurate distance, but the car needs to know how, how many meters ahead a particular object is. So in this case, you can spoof. That means you can hack the sensor and make it appear that there are trees and all kind of other objects in front of you. So in this case, the car doesn't know whether there's a real object or not, and so it will just stay in one place because it doesn't know that the road is clear. So this is a problem. Okay, so that's I just want to let you know. The other one is that these algorithms are very they're not robust. So that means that in all these cases, so this is a school bus, okay, and I think this is probably I don't know what this is, probably some kind of bird here, and then this is a temple, but you add a little noise to it, okay. So to the human, it's still a noise. I'm sorry, it's still a school bus, even though you added this noise. It's a blurry school bus. School bus. This is a blurry temple, but the machine learning algorithm now is confused because this noise addition, this is not good enough for it, and it thinks that it's an ostrich in all these three cases. So that's a bit scary, that with very little bit of uh, data distortion, we can fool the system into thinking that it's nothing to do with what it is. Okay, so again, the same idea here. AI tends to sometimes give you the wrong answer with very high confidence. In this case, it's 99.6% confident in the wrong answer, which is basically in these cases it thinks there's a cheetah here, which no human would think there's a cheetah here, right? And so these are a little bit more interesting. This is not an electric guitar, but the AI is very confident that it's an electric guitar, but to a human, I mean, it looks like an electric guitar, but it's not. Okay, this is also, it's not a baseball, but it just has stripes of red and white. But if you show this to the AI, it is 100%, almost 100% sure that it's a baseball. So that's a kind of they're easily fooled, okay, the deep neural networks at the moment. So high confidence in bad predictions. Okay, so I think I am going to wrap this up a little bit here. I think I want to give a little bit of guidance to the students and others who are interested in machine learning and AI. We talked about many of these interesting applications today. Okay, so first thing you need to do is most of the AI algorithmic side, of course, is practiced with a high-level language called Python. Python is a scripting language, very popular in the computer science industry, and it's quite easy to learn, I think, and it's very powerful. So learn Python. Okay, first thing is that. Second, there are many machine learning APIs. So you don't have to write these models from scratch. Okay, there are very similar problems that people have solved, and the beauty of the AI models are that you can reuse them for other problems. Okay, that's called transfer learning. You can solve one problem and transfer the learning aspect to another set of problems. So you just need to kind of know how to use these models. These models, you can think of it as like like Excel models. Most people don't know how all the math inside Excel works, but you can build a financial model or something like that, right? With an Excel spreadsheet. So think of it like that. That's how machine learning is going to be for the average layperson. Okay, unless you're a computer engineer and doing research there. So there is a lot of data sources available. Okay, so you should think about your own data source. Okay, so I saw a very inspiring one where a student was helping his father, I think in China. He was a farmer, and he had different kinds of vegetables, and so he helped classify and build a system to sort the different produce or the different things they were growing in their family farm. and put it into different buckets, okay, by using machine learning. Okay, so like carrots versus squash and other things. Okay, so by just taking a picture and then diverting it to the correct place. So look at your own data source. Okay. Also, this website here has a ton of very, very good data, some medical data, some from social sciences, and so it's very important. And finally, there is uh, no GPU is needed. So for inferencing, all you don't need to buy an expensive computer. In fact, this website here, colab.research.google.com, if you have a Gmail account, you can go in there and then you can start writing your own application on the cloud, and Google will run this thing for you and create the model and train it. And so it's a huge opportunity at no cost. You can learn and study and deploy your model. Okay, there are also some general purpose Google educational uh, computer science related things here in here, and then of course for coding also. Yeah, I'm not necessarily trying to only show you Google stuff, but these are the ones I have. But if you go and do a search, you will find a lot of these things. So my message is that almost anyone with a technical background in STEM, which is science, technology, engineering, and mathematics, okay, can start practicing AI. So what's next? I think this is my last slide. And before we take a few questions, deeper models need fewer examples in training. This is what needs to happen, and we will try to do that. For instance, a human child, okay, if or even a 3 to 4 year old, if you show him or her 5 pictures of a tiger, the tiger, they've never seen a tiger before, okay, only from books, just from pictures, then no matter whatever tiger you show after that, if you show 5 times 5 pictures of tiger, it's enough. The child learns this is a tiger, and he won't get it wrong. Okay, and it will learn. For computers right now, we need like at least about 500-600 pictures of tigers to teach it what a tiger is. So that's an important thing. So we need to improve that. Um, Again, the second one here is to become efficient, energy efficient to run on mobile devices. Currently, the models are too big and consumes too much power. So we need to fix that. That's the second aspect. Another third aspect is that reinforcement learning need to be improved. That is what I talked about, the child learning. That is unsupervised learning. Okay, learn about the world without going through a rigorous training. Um, so summarizing what's in a video clip is going to be possible pretty soon in a few years. Multimodal learning is not only images but other aspects about the context, about the social aspects of it, and then learn beyond individual data sets and abstract. Okay, and then finally we will see some commercial products, just like the face detector right now is incorporated into every cell phone, and in the next 10 years you will see some of these applications. Okay, thank you. All right, so that's my talk today, and I guess we have a few more minutes, about 7 minutes. So I will try to answer some questions if you are submitting them. So please submit if you have questions, except I don't know how to do this thing. Okay. Okay, I have one question. Is Oh yeah, so the question I have here is whether, I'm sorry again here, you put it here. Okay, good. Is AI and ML safe enough select as the career path? I mean, there is enough of a job market at the moment, right? Or should this be a sort of a hobby? Okay, so the question is that is this serious enough for us to consider? And the answer is absolutely. Okay, so look at this picture here. This is the growth projected worldwide. And so if the audience is in Sri Lanka, my main point is yes. Okay, please, it can be, it's a field that uh, is growing quite exponentially and no new infrastructure is needed. Most of the resources for it is free. And not only it should be a hobby, but you should be starting to thinking about solving real life problems. But there will be a lot of innovation in this field in the next few years, and also for entrepreneurship as well as for intrapreneurship, which is for companies that are fairly mid-sized or large-sized, but within their own organizations, they can make things more efficient. So for productivity, okay. So I would very much recommend everyone, because it's another thing that another revolution that will go on for another 10, 15 years. There is a lot of hype, but we also believe that some of the results are concrete. Like uh, the fact that we have algorithms that can do superhuman vision is the key thing. Okay, it can't have superhuman deductive capability yet. It doesn't have superhuman, probably language is also not superhuman. It's worse. If you have a chatbot, you probably get tired of it fairly quickly because it doesn't understand. Even the Apple Siri and Alexa are marginally useful for conversation. Yeah. Okay, so there is another one about Elon Musk's fear towards AI. Is it reasonable? And I think over the very long time, uh, I think I'm not going to comment on that. I think I'm not, I'm optimistic. I'm more of the opinion that just like the Industrial Revolution got rid of hard work that we had to do. We used to carry things with horses and bulls and other carts and other things, but now we have the internal combustion engine doing the hard work. In the same way, AI will offload a lot of tasks. That means our jobs are going to be different in 10 to 15 years. There may be no bus drivers, okay, where buses will drive by themselves and there'll be a lot less accidents. So there is some social aspect that we need to uh, resolve, and that can be done because you can even tax these AIs. Okay. Okay. So I think all right. So there's a lot of hype on deep learning with recent development. What are the other areas of AI that looks promising in the future? Okay. So the question is that there's been a lot of hype in the deep learning, but are there other areas? So AI is very ripe for innovation. Okay, deep learning is a technique that we can. It's a canned technique that we can apply very easily, many times to many problems. Okay, and I showed you kind of how to do that. But the reinforcement learning is more promising. That's a harder problem. So think of this as where physics was before Isaac Newton came around and wrote down some equations to describe physics. Before that, people knew the laws of physics intuitively, but they didn't have a good description. So my belief is that in the next 10, 15 years, we will have with the Newton or the Einstein for this field will come in and explain to us why it all works. Right now, we don't quite understand why it works. We have a intuition why things work, but I believe this field will grow, and so it's not a field that you can ignore. Okay, so please don't ignore it. Uh, okay, yeah. So recurrent neural networks. There's a question about, can you explain if using recurrent neural networks in an online learning aspect worth exploring. Yes, learning recurrent neural networks is definitely worth. Recurrent neural network algorithms are not at the level of a superhuman, okay, but recurrent neural networks is what allowed us to do things like predict this sort of thing here that I showed you here, this one here, okay, where image caption generation is done by recurrent neural networks. So that's the answer to that question. Yeah, I think we are running out of time, perhaps. Uh, okay. Uh, okay. So I think I am going to. I think we are done in about. It's probably 10 o'clock your time. So thank you very much. I think I'm going to wrap this up here. I don't know how to do that. Uh, okay. So okay. Yeah. Here. Yeah. Okay. So thank you. All right. So I'm going to. Close the Facebook page and stop the streaming. Okay, thank you very much. Again, uh, yeah, have a good night. Have a good night.